So in chapter 4, we're going to start out by taking a look at triangles that are no longer right triangles. That's different. Everything we've done so far has been based on a right triangle. The way we defined sine, cosine, and tangent were based upon a right triangle. Our unit circle values all pushed back into right triangles, and now we're going to look at what happens when the triangles aren't right triangles. And you're going to find that they push back into the right triangles a little bit as well, but there are some changes that we're going to make, some adjustments along the way to accommodate as well. So our first section is going to be law of sines, and then 4.2, the next section is going to be law of cosines. And so we're going to take a look at trying to figure out all the sides and angles of triangles when they're not right triangles. And there's two methods that we need in order to be able to do that, and those are these two sections. So our leading idea for today is the following. The law of sines helps us find an unknown side or angles in any triangle by trusting a consistent relationship between sides and their opposite angles. Even when the parts of the triangle are missing and triangles are not right triangles, we have faith that the law holds true and guides us to the right answer. Like faith in God, sometimes we don't have all the information about our lives or our future, but we trust God's promises and guidance are true and reliable. Just as the law of sines helps us to solve the triangle, faith in God helps us navigate life's uncertainties with confidence. Let's pray. Dear Heavenly Father, I thank you for an opportunity today to learn new material, to take a look at triangles that no longer fit into the nice, neat little box that we've been putting them in, but give us a broader perspective. Help us as we work today to be able to make progress and accomplish our goal. We pray in Jesus' name. Amen. So we'll start first with what is the law of sines. So if we have A, B, and C as the measures of the angles of a triangle, with opposite sides A, B, and C, then the following equation holds. So the little a on top is the side, divided by the sine of the angle A that's opposite on the bottom, and it works for B and for C. There's three pieces here that are equal, but we don't use them all at the same time. So if we're trying to find side B, we might be looking at these two at one time. Or if we're looking at sides A and C as our comparison, we might be setting up the equation with these two sides. Okay, so we take whichever two pieces of the three that we need at the given moment, and that's the ones that we use. The description here is that the ratio of the length of the side of the triangle to the sine of the opposite angle, that the side of that side is the same for all three sides of the triangle. So this ratio holds true. So when we solved triangles, oh goodness, I think it was back in section 2.4 is when we did that, when we were solving triangles. There's two different types of application problems or problems that we looked at. One of them was truly application problems where we were finding a certain length of like the shadow of a building or the angle of elevation to something. We found one piece of information. Y'all remember that? Okay, so those problems have sort of the difficulty that there's context involved that we have to navigate and make sure that we understand which piece we know and which piece we're looking for. But they have the advantage that you're usually looking for one thing. Then we had triangles where we were doing things called solving the triangle, and that meant we were finding all of the sides and all of the angles. So we didn't have any context involved, but we had to find more pieces of information. Nod your head if that sounds familiar. Okay, good. So that's actually where we're starting today, is finding all the sides and angles. So we're solving each triangle. So directions say solve the triangle, round lengths of the sides to the nearest tenth, and angle measures to the nearest degree. Okay, so that's telling us how we're going to round. And as a general statement now, we can't draw a right triangle. So don't do that. Draw some other arbitrary triangle that you wish. Okay, that was not good. Let's try it again. How about that? It's not a right triangle. It's not quite a triangle because I've got it a little bit down here at the edge, but we'll connect those and be good. We're going to write our A, B, and C in there. It doesn't matter where they go. There's absolutely no attempt as what we're doing this to try to put it to scale or anything like that. That's not the goal. Okay, we're just trying to give ourselves a picture to be able to put the pieces in. We want to remember that the side A, or the angle A, excuse me, that we've got listed here is going to be opposite the side A and so forth. So right now I've got some things listed. It says angle A is 87, so here's 87 degrees. Side B, which would be opposite angle B, would be down here is 75.9 yards. And angle C is 74 degrees. These are the three pieces of information. And in order to use law of sines, we actually have to be given enough to make this work. Now, this almost looks like we're not given enough. So what do I mean enough to make this work? Well, the reality is from this formula, we need to know a side and its opposite angle. And the way that I've written all these things in here, we don't actually have that given to us. We do not have a side given and its opposite angle. But we can find that very easily. So there's one piece of information in this that you don't need law of sines to find. You know how to do it. What piece of information can we find? The angle B, right? We can find that missing angle. So we're going to find that first. So we'll find this angle first. So triangle adds up to 180. So if I take my 180 and take off the 87 and the 74, I can find angle B. If you wanted to add the 87 and the 74 first and then subtract it from 180, you could do that too. So what do we get for angle B? 19. It's not very big, right? 19 degrees. This is one of the things that we were supposed to be finding. This is the measure of our angle B. Or we could actually write it the way that they've notated it for this section is they've just called it B. So we'll do it the same way. So B is 19 degrees, capital E. Okay, so while we weren't exactly given an opposite side and an opposite angle, we do have an opposite side and an opposite angle that we know, correct? And that's what we need in order to use the law of sines. We need this pair of information, and we have it. So with the law of sines, it tells us I can take the side length, which was the 75.9, and I can write it on top of the sine of the angle that's opposite its sine of angle 19. Okay, all good so far? We're now going to use the law of sines to find either A or C. So somebody tell me which one you do. Do you want to do A or C? A. Awesome. We're going to do A. So it is side A that I do not know. So I'm going to write that on top. And I'm going to write the sine of the angle A, which is 87, on bottom. This is algebra. I need to figure out what is A. What am I going to do to do that? We're going to multiply sine of 87 to both sides. So as you're using your calculator today and moving forward in this section, you need to make sure your calculator is in what mode? Degree mode. We're going to be using degrees in this section again. So as you're looking at this, could you have cross-multiplied? Yeah, you could have cross-multiplied. That'd be fine. But eventually, if you cross-multiply, you're going to still have to move that sine 19 that you multiplied by A back to the other side. So I'm not going to move it to start with, but if you did, it would be okay. So we're going to take sine of 87 degrees times 75.9 divided by sine of 19 degrees, and that's going to give us side A. What does that give us? Yep, 232.8. We're using one decimal because it told us to, right? Nearest tenth. And it has units. Yards. So that's side A. What do I still need to find? Side C. Now, when we were working with right triangles, we would have had a secondary option to find side C. We could have used the Pythagorean theorem. Can I use the Pythagorean theorem here? I cannot. Why not? I've got an A, B, and C. This is not a right triangle. So it doesn't matter if the letters are matching what I've seen before. It is not a right triangle, and the Pythagorean theorem only works when it's right triangles. But that's okay, because to be honest, if I just find side C the way I found side A, it's going to feel like I just did the same thing twice, right? Yeah. So as we come to this, I'll change colors so it distinguishes a little bit. We have that same 75.9 over sine 19, the same as we had before. But now we have the missing side C over the sine of the angle C, which is 74 degrees. And what would we do then to find side C? You bet. Multiply sine 74 to both sides. So then we need to do sine of 74 degrees times 75.9 and then divide by sine of 19. What do you get? What'd you have, Isaac?
224.1.
That's what I have as well. And it's yards, right?
Yes.
Yes. They all work that way. We need a pair, an angle side to start with, and then we're able to find the missing pieces. All right, let's take a look at one that's actually got application then, okay? So this is one where it just says solve a triangle, you find all the missing pieces. Here's one with some application. So it says to find the length of the span of proposed ski lift from P to Q, a surveyor measures the angle of DPQ to 25 degrees, then walks off a distance of 1,000 feet to R and measures angle PQR to be 15 degrees. What is the distance from P to Q? So first thing you probably better draw is what in the world a ski lift would kind of look like. And I don't think that you really need to be too involved in ski lifts to have this idea. But the ski lift goes up a mountain, right? So we're looking up a mountain. And a ski lift is just a device, right, that takes you up the mountain. So we're just going up the mountain. So from a perspective here, it tells us that we're going to have, let me see where I've got it listed. I'll draw it over here to give me the best space. Q, and we have our ski lift. This is a very tall, very, very sharp ski lift. It doesn't look like this for real. And then here's P down here. Okay, so you start at the bottom, and the thing would take you all the way to the top of the mountain. That's the way that would look like. And it tells us that the surveyor measured an angle measure down here. So, wow, my lines are not working out very straight today. Where we have a D over here, and this angle measure is supposed to be 25 degrees. It's definitely not a good picture to scale, but there's my 25 degrees. It says he walks 1,000 feet away. Now, you have to decide, where is he walking 1,000 feet? Well, we have two options. He's either walking 1,000 feet toward D, or he's walking 1,000 feet away from D. I mean, that's it, right? One of those two choices. So the question is, which one would make sense? If I moved toward D and I had a point down here that then went up to Q, could that angle that's created be 15 degrees? No. Why? Yeah, this 25 right here is my sort of reference point. Whatever's moving this direction is going to have to be a bigger angle. So I can't move this direction and then get a smaller angle. So I must be moving the other direction in order to get the smaller angle 15. Does that make sense? It's not really a scale issue, but it is an issue of comparison of angles. So my side that I'm looking at extending, if you will, or walking along is over here. Here's point D. And instead now I've created this angle here that goes up, and it's 15 degrees, the way that they've described it.
You mean R?
Oh, yes, R. Sorry about that. Thank you. And I was already worrying about the 1,000 feet. Here's my 1,000 feet that it said that we walked, and that is R. Okay. In order to draw in the angles, I kind of ended up drawing a triangle, right? I didn't kind of, I did. There's a triangle there. But we need to know what it is we're wanting to know, because again, with application problems, they're usually not asking us to solve the whole triangle. Don't do more work than they're asking you to do. Which of these pieces of information have they asked me to find? The distance from P to Q. So I'm asked to find, let me mark it in kind of orange, this one right here. This is what I'm asked to find. Basically asked to find the length of the ski lift. Okay? So this is the side I want to find. I have this side that I know, I have this angle that I know, I have this angle that I know. And in order to do something with this triangle, I need some sides and angles in this triangle. And to be honest, I only have this side and this angle in the triangle listed right now. What else can I find? This is using some geometry stuff from high school. What else in this triangle can I find with the information given? Angle P. So, and I think you mean this one down here at the bottom. Is that right, George? Yeah. I can find this angle. How in the world am I going to find this angle? Right. So these two angles are what were called supplementary angles. We actually talked about them back in chapter 1 as well. They have to add to 180. And since I've got 25 over here, I can know what angle P is. So what is angle P?
155.
Yeah. So 180 minus 25. It's 155. Got this angle 155. Anything else in my triangle that I can just know, because I still don't have a side and an opposite angle, right? I now have two angles, 155 and 15, and I have the 1,000 feet down here. But none of those are a pair of sides and opposite. I mean, none of these are opposite each other. They're all right beside each other.
Angle Q now.
I can find angle Q now. How am I going to do that?
180 minus 155.
Good. 180 minus the 155 that I just found and the 15 that was down there at angle R. So what is my angle at the top of my ski lift? 10. Now do I have a side and an opposite angle? I do. So what is the pair that I have that match, like that go together? They're opposites of one another. 10 degrees and 1,000 feet. Okay. The side length goes on top. That's the 1,000 feet. And sine of the angle, not just the angle, but sine of the angle goes on bottom. That's what law of sines says the ratio is. It's the side length compared to the sine of the opposite angle. And this will allow me to set up whichever other angle I want and whichever other side I'm trying to find. Well, the side I'm trying to find is this one right here that I marked, right? PQ. I need to compare this to its opposite angle. Now, the picture is harder to see than some of the triangles we've already drawn. But what angle is actually opposite side PQ? Is it P? Is it Q? Or is it R? It's R. This side right here is opposite that angle right there. A couple things you can do to think about that, because it visually doesn't really look like it's opposite, not the way we think about that, is it has to be the angle that it's not connected to. How about that? Right? It can't be angle Q because PQ is connected to Q, and it can't be angle P because PQ is connected to P. The angle it's not connected to would be what we would be considering the opposite angle, and that's the 15 degrees. Okay, does that make sense for everyone now? Okay, the picture doesn't picture the same way we were before, right? It looks different. But it is the sine of the 15 degrees that we're looking for. And it's side PQ, so I'm going to write it as PQ, but you're welcome to call it just X if you want to for now. That's fine as well, it doesn't matter. How am I going to figure out what is PQ? We're going to multiply both sides by the sine of 15 degrees so that these cancel, right? So we're going to take sine of 15 degrees times 1,000 divided by the sine of 10 degrees. And what are we going to get for the length of our ski slope or ski lift?
1,490.5.
Yep, and it's feet. Now, pause with me for a moment. We're going to make a remembered connection that we'd seen before. Do you remember we talked about bigger angles, bigger sides, smaller angles, smaller sides, right? That still holds, whether it's a regular, whether it's a right triangle like we've seen before, or one of these that are obtuse or acute. So when I have my angle 10 degrees at the top and it's opposite 1,000, and I'm now looking at an angle 15 degrees, I should be getting an angle a side that's bigger, right? So we do in fact get almost 1,500 over here. That is bigger. So at the very least, we know that that's a reasonable thing to have gotten. Make sense? Okay. And the good news is we don't have to find the third side because it didn't ask us to, right? So don't find more than you're asked. That's it for that problem. Now, there's something that's tricky that happens with law of sines. Depending on the information that you're given and what sides and so forth that you're working with, you can have something show up called the ambiguous case. So when can it occur? It can occur when we have side-side angle. Okay, so what does side-side angle mean? Well, it means that if you go around the triangle with the pieces of information you're given two sides sort of in order, and you're given the angle that's not in between them. Now, everything we've been given so far has been either two angles with a side between, right, like that, or two angles and a side, or it's being given two sides where the angle's in between them, right? So like over here, we were given multiple angles. So this is not the case of the ambiguous one because I wasn't given two sides. Over here, I was given, again, the same thing, two angles and one side. So I wasn't given the pieces of information that would have pushed me into this case. So you might remember from high school, at least I know this happened in my geometry class, somebody told you in looking at proofs usually, that you have all these proofs like side, and angle, side, angle, and side, side, side. And the one that you don't have is this one. You do not have side, side, angle, okay? And what my geometry teacher said is the reason is because if you turn it around, it's a bad word, okay? So it was a reminder, right? It was a reminder to know when it is you can't use something. Side, side, angle does not have a proofs property, and the reason is because of this. And this is why it happened, but you probably didn't see why it happened in geometry, so we're going to see why it happens in trig. So here's what could happen. There are 4 different scenarios that can happen when you are given 2 sides and the angle that's outside of them, okay? One thing that can happen is you could end up with no triangles at all. Okay, so imagine, right, you're given this angle at the bottom. This is the perspective they're giving you, is this angle at the bottom. And you're given the sides over here and over here. Okay, the angle is not in between the sides. It is possible when that happens that the angle's big enough that that third side that's opposite it, angle A or side A, just it can't connect, right? There's not enough down here. I don't have, it's not long enough. Okay, so this is one option. And when does that happen? Well, it happens, or descriptively, it happens when the side A is smaller than the height of the triangle. Okay, that's where that's happening. It also shows up when you're looking for it, like what will happen in trying to solve it is you get a sign of something, sign of B, that's bigger than 1. And we've looked a couple different times at, we'll do graphs. When we did chapter 2, we looked at graphs. And do you remember our sine graph bounced up and down, right? It's a wave pattern, and it bounced between -1 and +1. True? So I can't get a sine value that's, say, 3. It's outside that range window, right? I can't get them. So anytime I'm getting an angle here that shows up sine of B where I've got a value of sine is bigger than 1, it's not going to work. Second option is I could get one triangle. That one triangle could actually be a right triangle, that's possible, or it could be a non-right triangle, like the ones we've been working with so far today. So if it's a right triangle, that happens when the height and side A are equal to one another. Okay, that's the picture you're seeing here, right? The height and the side A are equal to one another. And that happens when the sine of angle B, so here's angle B down here at the bottom, angle B is equal to 1. Because the sine of angle B equaling 1 would give you a 90-degree triangle, right? Sine of 90 degrees or sine of pi over 2 is 1. We end up with a right triangle. The third option is that the side A is actually bigger than not only the hypotenuse, or not hypotenuse, the height, but it's also bigger than side B, okay? So we've got A bigger than B here. Again, B is down here, angle B. So the side length of A is longer than the side length of B. And when that happens, we actually end up with sine values that we're accustomed to. They're between 0 and 1, right? They're the ones that are supposed to work. So far, the only sort of problem is this one back here when I have 0 triangles. And it shows up very quickly that you know because you try to find an angle for something and it doesn't work. The sine of B is too big. The one that's tricky and the one that's actually called the ambiguous case is the third case here, or the fourth case if you count the last 2 as 2 of them. It's the case where you have 2 triangles. So take a look. Angle B, I'm still not saying right, angle B, good grief, side B and side A as listed before. I have A bigger than H, right? This length is taller than this length. But the problem that I have on this one is that it's between that and B, right? The length for A is between the height and B. It's not bigger than it like it was on the last one, it's between it. And when this happens, what we could have had is the side going like this down here and creating an obtuse triangle. So here's one obtuse triangle. Or we could have the acute triangle showing up on the outside here. So in other words, this value A has the ability, you probably have different, hinges on doors. Have you ever seen a hinge on a door that's broken and the door swings both ways, but it's not supposed to? Right? That's what's happening here. This value that's going from the top over here to the side or this side, it's able to swing both directions. And it works. Right? It works both directions. It actually lands down here and creates a triangle, and it lands over here and creates a triangle. I actually get 2 triangles. Okay, this is the hardest one to see happening from a computational standpoint. Obviously, we're going to see one, but this is the hardest one to see. The other 3 come about and are very obvious. This one's less obvious. All right, let's take a look. So it says 2 sides and an angle of a triangle are given. Determine whether the given measurement produces 1, 2, or no triangle at all. Solve each triangle that results. Round to the nearest tenth and nearest degree for sides and angles respectively. So just like we've been rounding so far. So every time I draw this, I'm going to draw it much like this first picture showed up right here. I'm going to draw it like this. We're going to start with this picture where it looks like the triangle might be incomplete. That's how we're going to start with our picture, okay? So we have, oops. This, something like this going on. All right, so this is angle, whatever the angle is they're giving me at the bottom, they call it angle A, just like I had from a moment ago. And it's 58 degrees. We've got side A, it's opposite it, it's 50. And we've got the B that's between those 2 pieces, which is 61. The pieces of information, whether they're called A, B, or C or not, different orders or whatever, they're gonna set up like this, okay? And we do have an angle in its opposite side. We're always going to have that as well, right? These go together. And it sets up just like the problems we were working with before. We're going to set this up as 50, because that's the side length, over the sine of 58. Okay, pretty good. So far, absolutely nothing looks any different except for I've drawn this wonky, incomplete looking triangle. Well, I have one more piece of information. It's side length 61. Side lengths go on top, so the 61 will go on top. And I will find the sine of the angle that's opposite 61. Since they called it B, I'll put it as sine of B down here as well. Now, on both of the examples we've done before, what we've actually had is we've had the angle here at the bottom, sine of some angle, and we've had the side missing at the top, right? And we've been able to multiply by the sine B to the other side, and we're done. Nod your head, because that's what we've done, okay? This one looks different, because now I have to find the angle that's trapped inside of sine, right? It's embedded inside of another function. So cross-multiplying actually is a pretty good place to do, thing to do at this place. So we're going to cross-multiply. We're going to have 50 sine of B, whoops, equals 61 sine of 58. I'd avoid doing anything in your calculator till the end. There's no need to trail along a bunch of decimals to keep accuracy or to lose accuracy. And we're going to divide by 50. So now I have sine B equals this. So here's the point when I would suggest go ahead and grab a calculator and let's write down, you know, a handful of decimals as we write this down. So what do you get when you take 61, multiply it by sine of 58, and divide by 50? I think Isaac's got it going on for us.
1.03461.
Okay, we're good. I'll go with 4 of them, that's fine. Sine of B is equal to 1.0346 approximately. That tells us something. What does that tell us? That value is bigger than 1, right? This is bigger than 1. Now, if you notice it at this point, this automatically tells you that there is no triangle. Now, let's say for a moment you're moving quickly or you've completely forgotten that that's how that works. You just blank out and you keep moving forward. Okay? Put yourself in that scenario for a moment. What would your next step be to find the angle B? We've done this in 2 or 3 different sections of material so far. How would I find angle B if I know that the sine of B is equal to something? Inverse sine. Thank you, George. We would do the inverse sine. So I'd like for you to take your calculator and tell it inverse sine of 1.0346. Somebody tell me, what does your calculator tell you back? Domain error. It tells you domain error. Does there anybody else say the same thing? Did you try it? Yeah. Sometimes they show up a little bit differently depending on your calculator. Math error. Okay, fantastic. And the reason it's saying that is because the inverse sine has a domain, and that value is that this input that we've put has to be between -1 and 1. And this input's bigger than 1. It's not going to work. So whether you remember it because you notice it on your own that this number is too big, or whether you recognize it because your calculator tells you domain error, either way, you're getting to the point that this does not work. There is no triangle that will work to do this. Okay, does that make sense? So this case is usually very easy to spot because the calculator will do it for you even if you forget along the way. Okay, all good? Okay, 0 triangles, that one's nice in terms of how it works out. Let's try another one. Okay, so all of the details are shown in the same way that the last one was. We're going to set this up with an incomplete looking triangle. Get that white back. Again, it tells us angle A, so I will call that angle A at the bottom. It tells us it's 42 degrees. It tells us the side A, opposite it is 15.6. And then the other side that they give us, which happens to also be B, is 8.1. This is the setup. They're always going to set up like this. So our equation sets up just like it did last time. Somebody tell me what my equation is going to look like. Fantastic. Okay. So Emily told us that. Is everybody good with that? Okay, what's the other side going to look like? 8.1 over sine B. Fantastic. What's our next step? Cross multiply. Okay, so we're going to have 15.6 sine of B equals 8.1 sine of 42. Now what? Divide by 15.6. Now that doesn't tell me my angle, but it tells me sine of my angle. So again, same thing as before. Let's get a decimal approximation. We'll get a bunch of decimals this time. Let's actually keep more of them this time because we're not going to get a number bigger than 1. So we might need more of them for accuracy.
0.347433.
Excellent. 6 is good. Okay. So we said what we were going to do last time. If we had forgotten, we're actually going to do it this time. What's the next step? Inverse sine, right? The opposite of sine. You can't divide by sine. Sine's not a number to divide by. It is a function to take the opposite of. The opposite of sine is inverse sine. So on the left-hand side, we get angle B. On the right-hand side, the inverse sine of, and make sure you're in degrees, of 0.3473433. What do I get for angle B in this case? What is it? 20. 20 degrees, right? Okay. Here's the determining factor. Here's how you can know whether or not you're in case 2, where it has 1 triangle, in which case we're done, or case 3, where there's a second triangle and we need to do something more, okay? Is you try and figure out if you can make it case 3. So let me show you what it looks like. This one's going to fail, so I want to show you how you would know if you did this that you failed, okay? Or that it failed. If there's another angle that would work here, because that's the problem, right? If we come over here to the ambiguous case picture, oops, there it was, is that there's an angle B here, B1, and there's an angle B2 here, right? And these two are the same. It's actually the same. This is an isosceles triangle that's showing up. But the angle that we're actually looking at is this one. These two angles would both actually work in this triangle and create everything else with the details proper. Like they would all be right. So we need to figure out if there's this other weird one right here that could work. We have essentially found this one, and we need to see, is there another one? Okay, and it's a really easy thing to do. Here's what you do. You take 180, and you subtract 20 from it. What's that? 160. And you ask yourself, is it possible that I could have an angle B that's 160 with the other information I've already been given in this problem? And the answer is no. TJ, how come?
Because the triangles are 180.
And?
It's 1 and 180.
Yeah, this 42 already would make that 42 and this 160 more than 180. I can't have another one. It's too big. Are you with me? Now, if I had gotten the case where it was small enough that it did fit, then I would have a second triangle, and we'll see that in a second. But this one's too big. It simply doesn't work. So all of this at the bottom is not actually creating the triangle. Now, we were actually supposed to find, the directions actually say to determine whether the given measurements produce 1, 2, or 3. So we just found out that this produces one triangle. And the reason we know is because we were able to try to see if it was 2 and it didn't work. Okay, so this is one triangle. Let's see what else the directions say. And it says round to the nearest tenth of degree and angles respectively. So we're going to find the rest of the triangle. We're going to solve the rest of the triangle. So we've got B, and we've got the 3 that were given to us. What pieces of information do we not yet have? C. Both the angle and the side, right? Which one's the easy one to find? The angle. Let's find the angle first. How will I find angle C? Okay, I'm going to subtract the 20 and the 42 from the 180. And what will angle C be? $118 is what I have as well. Angle C is 118. I need to find one more piece of information. It is side C. So I have the same thing I started with, the 15.6 over sine of 42. But now I'm doing problems like we started with today. I have the angle. Sine of 118 is going to go on bottom, and it's the side that's missing on top. So when I solve this, what do I need to do? I can multiply both sides by sine 118, and that will find side C. So, accuracy to 1 decimal, what is side C? 20.6. And did we have units? We did. Feet. One triangle. So, here's the interesting thing about this. If you totally forget that there's a possibility for 2 triangles even here, right, like that weren't part of the directions, you would have gotten this right. Now, it would have been kind of by accident because you wouldn't have actually tested to know for sure that you were right and there wasn't a second triangle. But by accident, you would have gotten the right answer, correct? Okay, so you will always be able to find one of the triangles if there are 2 present by accident. So let's see what happens when we actually have 2 triangles show up, because I want to show you obviously an example of both cases, or all 3 cases. So we're going to draw our same triangle that we were doing before, this sort of incomplete looking thing. This time they give us the angle C. That just means I'm going to put angle C in the bottom corner, okay? So don't go overthinking this. The angle that you're given, whatever its name is going to go in the bottom corner. And then side C is opposite it. It's 5.2 up here. And the third side they give you, again, no matter what it's called, is going to be between them at 8.6. So the picture sets up the same way every time for perspective. Doesn't matter what it's labeled. And the equation starts the same way. 5.2 is on top. Sine of 29 is on bottom. What's the other side going to say? 8.6 and sine of A, I guess, right? Yeah, A is what they call that one. Cool. How do we solve it? Cross multiply. So now we have 5.2 sine A equals 8.6 sine 29. Now what? Divide by 5.2. So sine of A is what? Let's get a bunch of decimals like we did before. It's not bigger than 1, right? We're not in case 0 triangles. We're in case 2 triangles because I've already spilled the beans.
0.0018000.
Try that again. I think you might be off by a decimal somewhere.
0.08715.
Okay, maybe I don't have this one written down then, because I am getting something different. I know it's gonna be wrong. I've got 0.8 something. That's what you have? Okay, so tell me what you have, Emily.
0.801.
Okay, I'll do four like this, 801, 801. Okay, so double check, make sure you're getting that because that's what I have as well.
That's what I have. I guess that's not what I said.
Okay, that's all right then. That's what you have, but not what you said. Cool. And how do we find angle A? I'm going to do inverse sine, right? And when I do that, I will get angle A, I think I have 53 degrees. Is that what you guys got? Okay. Now, we're going to do the same thing we did over here when it didn't work. We're going to see if there happens to be another angle that works. So the way that we do that is if there's a second angle, we'll call it A2, then it will be 180 minus the A that I already found. So 180 minus 53. So what's 183 minus 53? 127. Take a look at how 127 and 29 combine. How is this different than the last problem?
You can add another.
It works, right? It's smaller than 180. There's an ability already to be smaller than 180. I can add more to it and still be within the 180 triangle. That means I have a side A2. So for the purposes of clarity, I'm going to call this one, the first one we found, A1, and the second one A2. This is the case you don't want to be in. I mean, perfectly honest, because this means we have to find two triangles now, because these are two separate triangles that could have resulted with this information. So let's take the first one, A1, and let's find all the pieces of information about A1. And then we take the second one, A2, and we find all the pieces of information about A2. So for A1, we will set up, in fact, all of them we're going to set up 5.2 over sine 29. That's the same. But now I'm looking for side A1 over the sine of 53 degrees. We'll do just like we had done before. We're going to multiply by sine of 53. And that will find us side A1. Oh, I don't think I have my labeled correctly. So somebody's going to tell me because I've got, not A1. We already had A1. I'm sorry. Let me take a step back. That's the one we already know. Ooh, go ahead and turn that phone off. We getting it? Okay. It's okay. You're turning it off while I'm getting this fixed. I want to take a step back. I already have side A. I apologize. It's not side A I was wanting to find. It was side B that I'm wanting to find. Okay. So I need to find angle B1. That's my third angle. So if angle B1 is found using the 180, that's my cap, the 29 I was given, and the A1 that I already found, 53, this will give me angle B1. So what does this give me? 98. Okay, so this is angle B1, and then side B1. That's the one I was trying to find just a second ago, but labeled it wrong. So we'll have sine of 98 as the denominator, and we'll have that same 5.2 over sine of 29 as that denominator. We will multiply by our sine 98, 10.6. So in one of the triangles, B1, that side would be 10.6, and that's in our meters. Okay, so this is one triangle. It's subscripted 1, angle A1, angle B1, and side B1. Let's look at angle B2. So we have angle A2 is 127. So angle B2 would be 180 minus the 29 I was given and the 127 I found. So angle B2 ends up being quite small. It's 24 degrees. I didn't write this down, but let me write it down at the top. There are two triangles here. So this is side B2, angle B2. Let's find side B2. So for side B2, we would set it up to just like we found for side B1. So we'll have 5.2 over sine 29 equals B2. over sine 24. And we'll solve it just like we did. We're going to multiply by the sine of that denominator, sine 24. And this will find us side B2. So what is sine 24 times 5.2 divided by sine 29?
Why would it use the degrees of A2 to find B2? The side B.
So we don't have an A2.
Okay, so
Uh,
it's not.
So
That's just
we
saying
used-
that
we
this is
used-
like a triangle.
Cameron, we used A2 to find B2 here.
Okay.
That's what we used.
Okay.
So we used angle B2 to find angle B. We used angle A2 to find angle B2, and now we're able to use angle B2 in order to find side B2.
Okay.
Yeah. Do we have a value?
How many decimals?
4.4, 1 decimal on all of the sides. Yep, 4.4 meters. 4.4 meters. Okay, so we don't particularly love when we have this case, right? It's not great. But we actually have a very lovely formula for area that I can present in literally 2 minutes, okay? The area of an oblique triangle, take a picture if you're trying to write too much down, is always 1/2 2 sides multiplied times the sine of the opposite angle, sine of the other angle, the non-included angle. So B and C are the sides, we use sine of A. If A and B are the sides, we use the sine of C. So the formula works really nicely. These 3 things simply are not matching, right? As long as they don't match, the formula will hold for the particular triangle we're working with. So when we have something like this show up, notice I have A, B, C, right? 2 sides, 1 angle. So my area is 1/2. It's each of the sides, which are 20 and 50, times the sine of the angle, and I'm given 22. It's a very nice fact. It works very nicely. And if I didn't have all those pieces of information, I'd have to actually find them, right? The same way I've been finding sides and angles all day, right? And if I do this one, this says nearest square unit, so it means whole number. It's 187, and it is square feet. So be careful as you're working with that you include proper units, not feet, but square feet. And that puts a bookend on section 4.1. 4.2 is shorter. There's no ambiguousness. It's very straightforward.
Is 4.2 cosine?
Yes, 4.2 is law of cosines. All right.